Okay, everybody, it's time for some more geometry. Woo! We're going to do more with circles. So the circles on the board could be a disaster. So mentally prepare. We're going to imagine that they're circles, okay? Section 12.2, page 802. Here we go. Okay, so we have a circle. Not bad, huh? Starting off pretty well. That's exciting. And this is the center of my circle. This angle right here that comes from the center of a circle and hits the sides of the circle is called the central angle, which makes sense because it comes from the center. So the central angle, so what we're going to be talking about is a lot of things that have to do or are made by the central angle. So let's talk about the first one. The first one is a minor arc on page 802. A minor arc is an arc that's made by a central angle that's less than 180. We could define it that way. That's not how the book does, but we could define it that way. If this is A in the middle and this is B and this is C, this would be arc BC. And they'd use two letters and they'd use that little swoosh over it to show you that it's an arc, and that would just be from B to C or from C to B, really, it doesn't matter. Okay, and that would be a minor arc. The major arc in this case, if I'm still using the same picture, the major arc would be this one here that goes all the way around the other way. The way that they would write that down so you know which one they're talking about is they would say arc B, D, C. It starts at B, it goes through D and ends at C. That's how they would show you which direction they want you to go, okay? If they want you to go the little direction, they'll just give you the two letters. Go to the shortest distance between B and C. If they want you to go the other way, they'll put another letter in between so that you know you have to pass through that letter to get to the other one. And that would be a major arc, okay? Because it's more than 180. If it's just 180 specifically, exactly, that's a semicircle. Okay, so minor arcs, major arcs, and a semicircle is just half of the circle. It's the arc that's half of the circle. Okay, so let's look at example number 1. Before we do that, do we remember how many degrees are in a circle? 360. All right, so 360 are how many degrees in a circle, so we need to keep track of that. When we talk about arcs, we use degrees because the degrees around the circle, when we do circles, it's degrees. So arcs are also degrees. Okay, example number 1. The circle graph shows the types of music sold during 1 week at a music store. Find the measure, that's the little m, find the measure of arc BC. All right, well, let's look over at BC. From B to C is that teal color that's wrap, 13%. Did everybody see that? Okay. BC has a pie size of 13%. So what we're going to do is we're going to do 13%, let's turn it into a decimal, which is the section we're talking about, of the total circle, which is 360, right? So 13% of the total circle has a measure of 46.8 degrees. Yes, we do need to label with that little degree sign, okay? So the degree of, or the measure of arc BC is 46.8 degrees. Whatever percentage the little pie graph part has, we multiply it by a 360 because that's all for the circle, and that gives us the degree of just that little section. Okay, so arcs are measured in degrees. All right, let's look at page 803. Arc addition postulate. Let's say I had 2 arcs in this circle right here. I'm trying not to make a semicircle. Let's label it E. You probably could figure this out all on your own, but we're going to do it anyway. So this arc here, BC, arc BC, plus arc CE equals a total of arc BCE or BE. You could just say BE because it's a minor arc. You don't need to use those 3 letters, okay? So this one plus this one actually adds up to that whole thing. Shocking, I know, but wow. The stuff we learn is amazing, especially on a what is the day? Oh, I was going to say Monday because I'm recording it, but really you'll watch it on Tuesday, I guess. So, oh well. Okay, example number 2. Find the measure of arc CDE. So they use 3 letters even though it's a minor arc. That's okay. I like that actually because then I know exactly what they're talking about. So on the picture, they're starting at C, they're going through D, and they're ending at E, which on that picture is about right here, right? They want to know the measure of that one there. Okay, well, we know this angle. Well, I should maybe just draw another one because it needs to look like the one in the book. Okay, so here we go. Whoopsie. There it is. That's the first exciting circle there. Looks like an egg. All right. So we have a C and a D, and then E comes out about here, I think. Okay. And they want to know the measure of arc CDE. So CD we know is 90 degrees because this right here is 90. Okay. And then this right here, we have a angle situation that looks like this, and I know this is 18 degrees right here, correct? Remember, vertical angles would make this one 18 degrees as well, right? Because vertical angles are congruent. So as we look at that picture, I know this one is 90 and this one is 18. So the total, if this one is 90 here and this one is 18, our total is going to be 108 if I add those together, right? So the measure of arc CDE is 108 degrees. Okay, did you notice? I don't know if we maybe didn't talk about this, but the central angle right here and the arc are the same. Okay, if you have a center point and you have an angle, this central angle, remembers what that's called? The degree of that central angle is the same as the degree of the arc it makes. Okay, let's look at the bottom of 803 in the theorem 12.2.2. Okay, congruent central angles have congruent chords. Okay, well that makes sense. If I drew let's make congruent central angles. Here we go. Congruent central angles, I made them right here. Okay, here, this one and this one. All right, those are congruent central angles, right? They both are 90 degrees. Okay, I can actually draw a chord from where the angles hit the circle, like that. And I could draw another chord over here like this. Whoa. That's an awesome straight line right there. Okay, so if these two central angles are the same, this chord is the same as this one. Okay, they make congruent chords. If the chords are the same, the arcs are the same. And all of those work together. So if the arcs are the same, I know the chords will be the same. If the arcs are the same, I know the central angles will be the same. So they all kind of work together. They're all going to be the same thing. Central angles have equal chords, have equal arcs if they're equal angles, and vice versa. Okay, that's what they're talking about there on page 803. Okay, let's turn to example number 3. So if RS is congruent to TU, the chords there in that circle, we're supposed to find the measure of arc RS. Well, we know the chords are the same. Remember, we just learned if the chords are the same, the arcs are the same. So 3x would equal 2x plus 27. And you would just solve there and plug it back in to get what the measure of arc RS is. There's a lot of information in today's, and so I don't want to write down all the examples because I'm afraid we'll run out of time. So I'm just going to go through them, some of them. Okay, so example 3B on page 804. Circle B and circle E are the same. They're congruent, so that's good information. AC, arc AC, is congruent to arc DF, so they're going to have the same measure. We're supposed to find angle DEF. Okay, well, remember angle DEF, I'm trying not to talk too fast. Angle DEF is going to be the same degree as arc DF. So if I can find the arc, that's what the angle will be. So because I know those arcs are congruent, I can just do 5y plus 5 equals 7y minus 43. I can just make the arcs equal to each other, solve, and once I know what y is, I can plug it in to find the degree of the angle, right? I just plug it back into the degree of the arc because it's the same thing, okay? All right, so actually I think they showed those as the angles, but that's fine. So the angles are equal, we just make them equal to each other, plug it back in to get the actual degree. All right, on top of page 805, they have a chord there and a radius. So if in a circle, if the radius is perpendicular to a chord, it'll cut that chord in half and also the arc in half. Okay, so if in a circle, if I have a radius and it hits a chord at exactly 90 degrees, it cuts the chord in half and the arc in half, okay? And vice versa. If I know this is cut in half, I know that's a radius that's 90 degrees. All right, so let's turn the page. Oh, there's no example to go with that one. Oh yeah, example 4. Boy, yeah, I'm really out of it today. Example number 4, BD. Okay, so I know this is 2 and I know this is 3 in my little example number 4. I have a B, a D, a E, and an A. I think there's a little C in there as well, but I'm not going to write it. Okay, so I'm supposed to be finding, for example number 4, the length of this chord. Well, if I know the length from here to here, I can just times it by 2, right, to get the whole thing? Okay, so what I'm going to do is this. I'm going to draw a little radius here. Hey, does anybody know how long the radius is? Well, is this a radius right here? This is a radius right here. That's a radius, and that radius length is 5. So this radius length is 5 as well. Awesome, right? Okay, now, hey, guess what? I know you're going to be excited about this. This is a little triangle blown up in bigger proportions. This is a 3. This is a 5. How are we going to find that missing leg? You're right, the Pythagorean theorem. And if you know your Pythagorean triples, one of them is 3, 4, 5. It saves me from having to do it. 3, 4, 5 is a Pythagorean triple. So I know that this is 4 right here. Do Pythagorean theorem if you don't remember. So if that's 4, this is 4 also. So chord BD in total is both halves added together, right? So that would be 8. All done. Okay, that's what you're learning today. It's exciting stuff. I know you're really loving it. Circles are amazing. So, okay, I have to draw the joke for today because last week when I tried to show it to you, the picture in the book, that turned out to be a complete and total disaster. So I'm just going to draw it for you here. You'll love it because it's like a plexer. Okay, and it wants to know what is the hidden math term. The hidden math term right here. Go. I know you all said it at one time. You guys are so good. It's circle graph. Have a great day. Bye.